Let's learn about acid-base regulation. To maintain homeostasis, intake production of H plus, net removal of H plus must be in balance. Precise regulation is needed because all enzymatic activities are influenced by H plus concentration. Normal H plus concentration is 0.00004 equivalent per liter. pH actual H plus concentration. Acid any compound which forms H plus ions in solution. Proton donors, for example carbonic acid, releases H plus ions. Then base any compound which combines with H plus ions in solution. Proton acceptor bicarbonate HCO3 minus accepts H plus ions. Acid base balance, normal pH 7.35 to 7.45. Then acidosis will be a condition. So acidosis, physiological state resulting from abnormally low plasma pH, excess addition of H plus. Then alkalosis, physiological state resulting from abnormally high plasma pH, excess removal of H plus. Then acidemia, plasma pH less than 7.35. Alkemia, plasma pH greater than 7.45. Acids, volatile acids produced by oxidative metabolism of CHO, fat, protein, average 15,000 to 20,000 moles of CO2 per day excreted through lungs as CO2 gas. Fixed acids, two kinds of acids are there, volatile acids and fixed acids. M equivalent per kg per day. Acids that do not leave solution once produced, they remain in body fluids until eliminated by kidneys. Sulfuric acid, phosphoric acid, organic acid are most important fixed acids in the body, are generated during catabolism of amino acids, oxidation of sulfhydryl groups of cysteine, methionine, phospholipids, hydrolysis, nucleic acids. Response to acid-base challenge, chemical and base buffer system, the lungs and kidneys. Buffers, first line of reference, greater than 50 to 100 m equivalent per day. Then two most common chemical buffer groups are bicarbonate and non-bicarbonate. Non-bicarbonate in the sense HB, protein, phosphate. Blood buffer system acts instantaneously, regulate pH by binding or releasing H plus. Body buffer system, buffer a solution consisting of a weak acid plus its conjugate base. H plus plus buffer is equal to H buffer, remain unassociated or dissociate back. When H plus increase, reaction is forwarded towards right and vice versa, thereby minimize H plus concentration. So buffering is the primary mean by which large changes in H plus concentration are minimized. The most effective buffers are H2CO3, H2PO4, plasma protein or HB. Carbonic acid bicarbonate buffer system is the first one. So carbon dioxide will be there. So most body cells constantly generate carbon dioxide. Most carbon dioxide is converted to carbonic acid, which dissociates into H plus and bicarbonate ion. Prevents changes in pH caused by organic acids and fixed acids in ECF. Cannot protect ECF from changes in pH that result from elevated or depressed levels of CO2. Functions only when respiratory system and respiratory control centers are working normally. Ability to buffer acids is limited by availability of bicarbonate ions. It's a water solution if it is a water solution containing two ingredients, HCO3 minus HCO3 weak acid plus NaHCO3 weak base. H2CO3 gives H plus plus HCO3 minus, NaHCO3 Na plus plus HCO3 minus. CO2 plus H2O, etc. are produced like H2CO3, H plus plus HCO3 minus, NaHCO3. And a strong acid like HCl is added. HCl, H plus plus Cl minus, we know that dissociation will be happening. Then H plus plus HCO3 minus giving H2CO3, that's a weak acid. Then H2O plus CO2. Excess CO2 stimulates expiration. When a strong base like NaOH is added, NaOH plus H2CO3 gives NaHCO3 weak base plus H2O, stops expiration. Some proteins in the body also can function as bases. Some amino acids that make up proteins have net negative charge that readily accept H plus, for example HB. Proteins are the most plentiful buffers in the body because of their higher concentration, especially within the cells. pH of cells is slightly lower than ECF, so the buffer system within the cells help to prevent the changes in the pH. 60 to 70% of the body's total buffering capacity by body fluids is inside the cells. Another factor contributing their buffering capacity is the fact that the pKa of many of the protein systems are fairly close to the intracellular pH. The hemoglobin buffer system. CO2 diffuses across RBC membrane. No transport mechanism required, as carbonic acid dissociates, bicarbonate ions diffuse into plasma in exchange for chloride ions. Chloride shift. Hydrogen ions are buffered by hemoglobin molecules. HHB is the only intermediate buffer system with an immediate effect on ECF pH. Helps prevent major changes in pH when plasma POCO is rising or falling. Then phosphate buffer system consists of anion H2PO4 and cation HPO4 minus. H2PO4 is a weak acid and HPO4 minus is a weak base. pKa about 6.8. Works like a carbonic acid bicarbonate buffer system. It is important for buffering pH of ICF. Limitations of buffering system include provide only temporary solution to acid-base imbalance. Do not eliminate H plus ions. Supply of buffer molecule is limited. When a strong acid like HCl is added, HCl, H++, HPO4 minus, H2PO4, HCl, NaCl, H plus, Na2, HPO4 gives NaH2PO4. That's a weak acid. No, it's a NaH2PO4 plus NaCl. When a strong base like NaOH is added, NaOH plus NaH2PO4 gives Na2HPO4 plus H2. That's a weak base. Respiratory acid-base control mechanisms. When chemical buffers alone cannot prevent changes in blood pH, the respiratory system is the second line of defense against changes. Eliminate or retain CO2. Change in pH are rapid, occurring within a minute. Renal acid-base control mechanisms. The kidneys are the third line of defense against wide changes in body fluid pH, movement of bicarbonate, retention or excretion of acid. Then generating additional buffers. Long-term regulation of acid-base balance may take hours or days to correct this imbalance. Renal regulation of acid-base balance. Role of kidneys is preservation of body's bicarbonate stores accomplished by reabsorption of 99.9% of filtered bicarbonate, regeneration of titrated bicarbonate by excretion of titratable acid, mainly phosphate, ammonium salts. Renal reabsorption of bicarbonate, proximal tubule about 70 to 90%, loop of Henle 10 to 20%, distal tubule and collecting ducts 4 to 7%. Factors affecting renal bicarbonate reabsorption: filtered load of bicarbonate, prolonged changes in PCO2, extracellular fluid volume, plasma chloride concentration, plasma potassium concentration, hormones like mineralocortico-glucocorticoids. If secreted, H plus ions 440 m equivalent per day combined with filtered bicarbonate 4320 m equivalent per day. Bicarbonates is reabsorbed. 80 m equivalent is excess. If secreted, H plus ions combine with phosphate or ammonia, net acid excretion and generation of new bicarbonate occur. Then net acid excretion. Hydrogen ions are secreted into tubular fluid along proximal convoluted tubule, distal convoluted tubule and collecting duct. Titrable acidity occurs when secreted H plus encounter and titrate phosphate in tubular fluid. Refers to amount of strong base needed to titrate urine back to pH 7.4. 40%, 15 to 30 m equivalent of daily fixed acid load, relatively constant, not highly adaptable. Then ammonium excretion occurs when secreted H plus combined with NH3 and trapped as NH4 salts and tubular fluid. 60% of daily fixed acid load, very adaptable via glutamate induction. Ammonium excretion, large amount of H plus can be excreted without extremely low urine pH because pKa of NH3 NH plus 4 system is very high, 9.2. So that's all about this acid base balance. Thank you for listening.